Okay, now that we know something about datum reference frames, we can put them to use with orientation tolerances. We'll define what we mean by orientation tolerance and then look at a specific example of one called perpendicularity. And then we'll bring in the material condition effect and how that might be used. When we're talking about orientation, clearly we're looking at how something relates to something else. In terms of our design spec, we're looking at individual features and seeing how they relate to other features. The other features being the datum reference frame. And that datum reference frame, after it's constructed, can be used to say something about the part feature. The geometry that we're trying to control is the focus of the geometric tolerance zone. So we might be trying to control the actual surface in terms of its orientation, a line, for instance, an axis, or a plane, perhaps a midplane. Again, we're trying to control this geometry using the geometric tolerance zone. We also know that we'll have deviations in feature orientation when we produce this part. And this will be affected both by its shape. For instance, if I've got an axis that's curved, as well as the orientation in which that feature was created. Indirectly, by controlling the orientation, we will affect the shape of the object. So here are the types of orientation tolerance. The two special cases which are quite common are perpendicularity and parallelism. And clearly, if we're talking about perpendicularity, we're dealing with a relationship that is pi over 2. And if it's parallelism, that relationship is defined by the angle pi. Angularity would just be the general case, any angle that's specified, and again, this angle would be specified as a basic dimension. So we don't have to specify the angles for perpendicularity and parallelism. We will just use the symbols, and that will tell us which relationship we're trying to enforce. The orientation tolerance zone requires a datum reference. And therefore, if you don't see a datum reference in the feature control frame, that's a problem. And we'll emphasize that throughout the discussion. The shape of the tolerance zone, again, as you know, you need to be able to define the attributes of the tolerance zone, and shape is one of them. We're going to see two parallel planes, or a box, trying to enclose a planar surface, or two parallel lines trying to enclose a line geometry, or a 3D tolerance zone, a cylindrical tolerance zone that encloses an axis. The tolerance zone location, again, another attribute of the tolerance zone, is floating. In other words, it can be anywhere. And we'll see that in our examples. The tolerance zone orientation, clearly it is constrained by the datum reference frame. So we're going to orient the tolerance zone according to the feature control frame with respect to our datum reference frame. Let's look at the simple case of perpendicularity. Here we're going to look at a feature, again, over the entire length of that feature, and ensure that whatever the geometry is, it lies within a tolerance zone of width t. So here we see two parallel planes, here we see a cylindrical tolerance zone, here we see two parallel lines. The meaning of t varies depending on the geometry. Here it's the distance between those two lines, here it's the diameter of the cylindrical tolerance zone, here it's the distance between the two planes. And of course, whatever this geometry is has to lie within that tolerance zone. The tolerance zone is what's oriented perpendicular to the datum, one or more datums. Well, if we look at the perpendicularity of a surface, and for right now it'll be a planar surface, all points have to lie between those two parallel planes. Again, separated by a distance t. You already know how to determine t. In this case, it's a static tolerance, and we see that every point has to be between those two planes. Now, note what we said before, the location of the tolerance zone does not matter. So I could shift, and again, we're looking from the top here, so I've got two parallel planes. I could shift that upward in this direction, as long as the surface lies between those two planes, or I could shift in this direction, What I have to maintain is its perpendicularity to datum A, which, as you know, is a planar surface here. So I can't violate that relationship, but I can certainly move that tolerance zone up and down as long as we maintain perpendicularity, and of course I can translate it left and right. What if we have multiple datums? What's the effect? So in the previous case it was just datum A. Now we're going to add datum B, the bottom of the plate, and when we do that, we can see that datum A, because it's primary, is going to set the orientation. In other words, it will have the greatest effect on the orientation. And therefore, what we're saying here is we're not only relating this surface, to this surface, but we're also relating this. In fact, this will have the most effect on the orientation. And then, as you know, we're going to bring in a surface plate here representing A to establish that datum reference frame, and we should probably show the that feature there and here. And so now this has to be maintained perpendicular to B, then A. So we're adding an additional constraint, and we're adding a different type of impact. We're concerned about the relationship to the bottom of the plate as well. Again, the size of the tolerance zone is the same, the shape is the same, we've just changed the constraint. We can talk about the perpendicularity of an axis based upon its relationship to one or more datums, but when we do that, we're implying, of course, we have a cylindrical feature. And if it's a cylindrical feature, then it's a feature of size, so you should know that the mating envelope would have to be used to determine, and that's what's indicated by this green outline here. We've created a mating envelope that defines our axis. And now we're going to take that axis and compare it to our cylindrical tolerance zone. So it has to be contained within our tolerance zone that has a width t. And we can see here in this case, t is equal to 0.01. So we have a static tolerance zone. Again, we can move our tolerance zone. By that, what we're really saying is my feature could actually be over here. And yet, it could still be perpendicular to datum A. Datum A, of course, is this bottom surface, so we have to establish that first before we can orient the tolerance zone. So I don't care about the location of the feature. I only care about how it's oriented with respect to A. Again, over the entire length of the feature, we have to check the axis. Well, there's a special case here, and that is when you want to look at the surface and not the axis. So when that's true, we're going to contain all surface elements. In other words, similar to straightness, where we contain the surface as independent cross-sections, an infinite number of those, we'll do the same thing here with two parallel lines. Now, how do you know you're dealing with the surface and not the axis? Well, you can see right here, we've got a note at the bottom saying each radial element, and that would have to appear. Your other hint is the fact that there's no diameter symbol. Okay, so we're dealing with the surface and not the axis. So we've got 0.01, that would be the separation between these two lines. And when we travel around this cylindrical feature, each time we move those two parallel lines, it's independent, just like we did with straightness. What's different about this than straightness is we orient these two parallel lines with respect to our datum reference frame, in this case datum A. So it kind of looks like straightness, except we've got an orientation constraint. Clearly it does affect the shape. There is a secondary effect on the shape of this feature. Because we're constraining orientation, it's also going to control shape to some extent. Well, what happens when we have a material condition on the feature? And we've seen this before. Here we've got our M, and that's indicating to us that as the feature deviates from material condition, what we're going to do is add additional tolerance zones. So we have this dynamic tolerance situation. And that's reflected, as we've done before, by adding in that deviation. So we have to measure the amount of deviation from material condition that's indicated by D here. And we do that by using the mating envelope, as you would expect, and I contract the smallest cylinder around this feature to determine what D is. Then I subtract the maximum material condition, which we can determine from the feature's dimensional tolerance. So my total width here is unknown until we actually make this part. Now, a slight nuance here that we've seen before is A is now attached to the dimension line, so you should be able to recognize this as a feature of size, and therefore we're not talking about this surface, but we're talking about the midplane cutting through the cylinder here. So here I've indicated datum A would have to be established by taking the mating envelope, which would be the smallest box that we can fit to enclose the top surface and the bottom surface. We're not talking about a cylinder now. We're talking about two parallel planes to enclose those two surfaces. Once we've defined that, then we can determine where A is and, of course, orient our tolerance zone with respect to that. Well, we could have material condition, as we've discussed before, both on the feature and on the datum, or actually one or more datums. In this case, datum A. Datum A, of course, would have to be a feature of size. If you see an M there and A is just a surface, that would be a problem. In other words, something is not right with the specification. But we see an M for the feature, we see an M for datum A, and now we have to take both of those into consideration when we're determining the width of our tolerance zone. So in this case, we have additional tolerance, not only due to the feature deviation from its material condition, but also due to the datum's deviation from its, or I should say the part feature corresponding to the datum, its deviation from its material condition. So its material condition, again, maximum material condition, largest in this case because it's solid, 0.26. This hasn't changed from the previous example, still 3.6 here. And now we have this additional tolerance more than we had in the previous example. Principles are still the same. Mating envelope used to determine A. So I have to actually have a part, measure A, then I will create a midplane here. Then I will orient the tolerance zone with respect to that. I will find D by mating envelope, smallest cylinder that contains the feature. Then I can measure D, and then I can determine if its axis over its entire length fits within that tolerance zone. Again, the tolerance zone has no position constraint. It could end up over here, the feature could be anywhere, and yet it could still be perpendicular to datum A. So at this point, you should understand the concept of orientation tolerance, specifically perpendicularity, and how to orient that tolerance zone so you can say something about the geometry that we're trying to control. And finally, you have to have a datum reference frame. If the datum reference frame is missing, then that's a problem that needs to be resolved. So we've got this requirement. If I'm going to have an orientation tolerance, you must have a datum reference frame. There is no fixed position for that datum reference frame because we're not trying to control position, and therefore it can move anywhere as long as we can contain the geometry. Our tolerance zone shape, we've seen rectangle, cylinder, and a box corresponding to two lines, a cylinder and two planes. The width can be affected by material condition, both for the feature as well as the datum, and orientation tolerance will indirectly control form. It will have an effect on shape.